All right, so this video is going to be all about writing electron configurations and orbital notations so that you too can tell people all about where electrons are around an atom. So the thing to start off with, remember for your electron configurations that those blocks on the periodic table that I have talked about previously, they all have some meaning, right? The S, D, E, and F block, right? They're useful for electron configurations and orbital notation. If you remember in the last video, I did say that they tell you where the outermost electrons are located as far as subshell, and that's going to come in really handy when we start looking at writing out electron configurations. So things to know before we jump into writing these. There are 4 types of subshells, S, P, D, and F. Each subshell holds a different number of orbitals, right? S has only 1 orbital, P has 3, D has 5, and F subshells have 7 orbitals, right? And each orbital can only hold a maximum of 2 electrons, meaning that in an S subshell, there can be a total of 2 electrons. In a p orbital, right, or a p subshell, if each orbital can hold 2, there can be a maximum of 6 electrons. In a d subshell, since there's 5 orbitals, you can have a maximum of 10 electrons. And in an f subshell, because there are 7 orbitals, you can have a maximum of 14 electrons. The blocks of the periodic table indicate which subshell the highest energy electrons are in, right? Those furthest from the nucleus. And so, for example, the electron configuration for a p block element will always end with electrons in the p subshell. Lovely how that works. So, the Aufbau principle. This states that electrons will fill atomic orbitals from lowest to highest energy. And what this means is that electrons will fill the orbitals around any atom in the same order, and that all orbitals of lower energy must be filled before electrons can fill higher energy orbitals, right? So that means energy levels will always fill in order 1, 2, 3, 4, etc. Not want to write a C here for some reason. I'm not quite sure why. There we go, etc. So it will never fill 1, then some 4, then maybe a little 7, then go back and fill some 3, right? That's not what happens. It always fills in order. You will always have subshells and energy levels filling in order from lowest energy to highest energy. It's the building up principle. So here are some graphics to help you remember in what order everything fills. There's this really nice one over here with the arrow kind of going through, right? Like some sort of map showing you that it's filling 1s, then 2s, 2p3s, 3p4s, 3d4p5s, 4d5p6s. Then we start filling some f, 4f, 5d, 6p7s, and so on. There is no currently 8s. That does not exist as far as we know, so you will never have to worry about 8s. Over here, this is another little graphic that helps you remember. It starts down here with 1s at the bottom. Not a very good arrow, but I'm going to go with it. And then works up, right? 2s, 2p, 3s, 3p, 4s. But then you will notice that 3d is in between 4s and 4p, which means 4s fills first, then 3d, right? Just like over here. 4s, 3d, 4p, right? Same thing. So these are just two visual ways to help you remember in what order everything fills. But here's the cool thing. The periodic table is built in that order, right? So the periodic table here is kind of built in that order. If we look back and remember S block, right? Over here, first energy level, 1s, it fills first. Technically, this is 1s2, despite the fact that it's over in the P block, but we're going to go with it. All right, 1s, first electron, second electron. S is done, right? Because if we remember back, S, right, has one orbital. Any orbital holds 2 electrons. So in 1, since there's only one S, we can only have 2 electrons. One here, one here. First energy level, done. That's it. So, electron configuration, right? We're going to look at carbon. First thing to do, find carbon here. Great, carbon. Well, look, its atomic number is 6, which means that it has 6 protons, but also that it has 6 electrons total, right? So we'll have to remember that. The block that it's in, it is in the P block. And it is in row 2, meaning that its last electrons will be in 2p, right? And now we'll just go through. This is the electron configuration, and I will talk you through how we get there, right? So we know that you have to start from the very beginning, right? Electrons fill from lowest energy to highest. So every single electron configuration for any element on the periodic table will begin with 1s. And so in this case, we have 1s1, 1s2, right? 2 electrons in the 1s. That is what this term means. Energy level 1, energy level, subshell, and electron, right? So that means first energy level, S subshell, is holding 2 electrons. We know because we know that every single space up to carbon has to be filled. So we have 1s with 1 and 2 electrons. We then move to 2s, right, with our third, fourth electrons. We say 2s has 2 electrons in it. We then move into the P block. And to know how many electrons in this last space, we count in 1, 2. So we know 2p has 2 electrons, which are our 5th and 6th electrons in here. Right? So if we count up the number of electrons, 2, 4, 6, which, great, we have the right number of electrons. If we look, row 2, so the last electron should be in the second energy level. Fantastic. This will not always be true. We'll talk about this in a second in some examples. And it's in the P block. So its last electrons should be in a P subshell, which they are. Great. Let's take a look at some other examples. Okay. So if we look at, let's say, magnesium, we'll walk through this again, right? Magnesium. It is number 12, right? So atomic number, that is not an N. Erase that. Atomic number 12, right? So that means it has 12 protons. It will also have 12 electrons. So after we write this out, we should have 12 electrons. We look, it is in the S block. So block S, and it is in the third energy level, right? So we're going to start out just like we did last time. We start at the very beginning. That's a very good place to start. We see in S, first energy level, we have 1, 2 electrons. We know 1s2. In 2, in S, we have 2 electrons. 2s, 2. In 2p, we have electrons 5, 6, 7, 8, 9, and 10, which means we have 1, 2, 3, 4, 5, 6, right? So we're going to say 2p, 6. Then we come down here, our third energy level, right? Where we are in the S block. We have our last 2 electrons. We're in the S block, 2. And we look, 2, 4, 10, 12. We have the right number of electrons. Fantastic. So let's try one in the D block here, right? So D block, we're going to look at iron. Here's where things are a little weird. So if we go back real quick to look at this, right? Keep in mind that 3D, right, is the first D you encounter. So this right here starts 3D, right, with scandium. In the F block, where you have F energy levels, right, this first one is 4F, right? There's no secret to this. You'll just have to remember that the D's start at 3D, the F's start at 4F, right? So unfortunately, like I said, no real trick. You'll just have to remember. So if we come back to this, right, we're going to look at iron. So we've got iron. Its atomic number is 26, which means we are going to have 26 electrons in total. We know that it is in the D block, and that its energy level, right, is going to be 3. It is in 3D. Because remember, we said the first D is 3D. And this would be 4D, 5D, D. Okay. So just these out of here. Okay. So then we'd start it and finish it just like our other, right? We look to start here, 1s. We know that we've got our first 2 electrons here. We have 1s2. We look at second energy level. We know we have 2 electrons in 2s. We look here, 5, 6, 7, 8, 9, 10. We know we have 6 electrons in our 2p. Look here, got 11, 12. So in our 3s, we have 2. Here, 13, 14, 15, 16, 17, 18. Right, in our 3p, we have another 6. We look here, 19, 20. So in 4s, we have 2. And then we count in 1, 2, 3, 4, 5, 6. So in 3d, there are 6 electrons. If we add these up, 2, 4, 10, 12, 18, 20, 26. Look at that, the right number. So that is how to do electron configurations. if you are looking at simply the last term of the electron configuration, right? Like let's say we are looking for sulfur. We look at sulfur, the last term of the electron configuration. Well, we know that it is in block P, right? Sulfur right here, the P block. The energy level, 3. So we know that the last term, right, is going to be 3p something. Then we count in from the end. 1, 2, 3, 4. So we know the last term, right, is going to be 3p4. So doing full electron configurations, this might be useful. You can kind of work backwards, right, from your last term, knowing that that's going to be the only one that is not full, and you just make sure everything is full up to that. Or if you were ever asked to do the last term, then that's an easy way to find it. You find the block, the energy level, and you count in from the beginning of the block, right? Not the table, but the beginning of the block. Okay, so now on to orbital notation. So the first rule that goes along with orbital notation is going to be Hund's rule. So every orbital in a subshell must be filled with one single electron before they will begin to pair. I always tell people to think of a public bus, right? We're talking pre-COVID here. Because on a public bus, no one's going to want to sit next to some smelly weirdo, right? Like me, for instance. If you saw me on a bus, you'd probably be like, I don't want to sit next to that guy, so I'm going to go over here and take this completely empty seat before being forced to double up with some crazy stranger that you see on a public bus. So when we look at orbital notation, right? We're going to use carbon as our initial example here. These are nearly identical to electron configuration, except the orbitals and electrons are shown drawn in. So this is where Hund's rule comes in, right? Because like we have our 2p2 here, so we know we have 2 electrons in our the subshell, and they're going to go in separate orbitals, right? Because each of these boxes represents an orbital. And no, pen is not working again for some reason. There we go. And so each of these boxes represents an orbital. So before pairing them up, right? Because you don't want to do this, right? That's no good. That would be wrong. You are going to want to have them fill individually first, right? So it looks basically the same, except we're writing out the electrons, and I will show you an example or two. So let's say, and I'm not going to pick a super long one because I don't want to be drawing boxes on here forever. Let's take a look at sodium. All right, so we're going to go through again, sodium, and we'll figure out, right, atomic number. And its atomic number is, what is it? 11. 11. Okay, so 11. That means it's going to have 11 electrons total. So we're going to have 11 of those little arrows. It is in block S, right? So its last electrons are going to be in S block. And its energy level that they're in is 3, right? We start out. We're going to draw those boxes just like we saw 1s, right? This box, we know that there's 2 electrons in 1s, right? Our electrons 1 and 2. Then we move on to 2s, right? And remember that we know how many orbitals are in here because earlier in this video we talked about how s holds 1 orbital, p holds 3, D holds 5, F holds 7. We know that our next 2 electrons are in our s orbital, show them there. Then we're going to move on to 2p. Remember, p subshells, 3 orbitals. I know this is a lot to remember right now, but if you do it a couple times, and I promise you it will be easier. So this is full, right? We've got a full energy level here. So we're going to say, I'm just going to put all 6 of these electrons in here. We get down to 3s, or 1 orbital, and our 1 electron, right? Making our last electron there. So let's do one more. Let's take a look at, let's say, fluorine, right? Fluorine, atomic number 9, going to be in the P block, and its energy level is 2. Okay, so again, right, every single time we start out with 1s, and we know that we have 1s full, right? We've got our first 2 electrons there. We come down to 2s. S has 1 orbital. We know we've got our next 2 electrons there. And then we get to 2p, where fluorine is. Now we have 1, 2, 3, 4, 5 electrons in 2p, right? Which are 5, 6, 7, 8, and 9th. So we make our 3 orbitals. And this time I'm going to draw 1, 2, 3, 4, 5. And I always do that just to remind myself that I'm filling them one at a time before pairing, right? And so this is how you do orbital notation. It's pretty much just like electron configuration, except you're showing where exactly the electrons are. They fill in the exact same order, and they fill one in an orbital before pairing up. So last thing we're going to talk about here, isoelectronic atoms. This is when 2 atoms, neutral or ions, have the same electron configuration, right? Isoelectronic. So if we look here, all right, we've got neon. This is its electron configuration. Then we've got a nitrogen ion, right? Or actually, technically, I should say nitride ion because it's negative. When you add 3 electrons to a nitrogen atom to make the nitride ion, you end up with the same electron configuration as neon, right? Turns out that when you have a magnesium ion, right, taking 2 electrons away from magnesium, again, you end up with the same electron configuration, right? Because the neutral configuration here was this, and the neutral configuration here was like this, right? But because we added 3 electrons here, right? That's what happens when you make a negative ion. You're adding electrons. And we took away 2 electrons here, right? Because that's what happens when you make a positive ion. We end up with the same electron configuration as neon. So that is isoelectronic atoms. Anytime you have atoms that have the same electron configuration, they're going to be called isoelectronic. Okay, so what to remember here? Any orbital can only hold 2 electrons maximum. The block where an element is found on the periodic table will always indicate where its last electrons will be found, right? So the last term in the electron configuration. Electron orbitals fill one at a time before pairing, right? Think people on a bus. And the electron configurations have only letters and numbers. Orbital notations have the boxes, or sometimes you'll see them as lines, and the arrows, right? Okay, so hopefully this makes some sense. We will talk more about this in class, and you can ask me any questions during the week through email, or if you need even more help than that, let me know, and we can find a time to talk about this. So thank you, and I will see you back in class.